GT Intelligence Camera presents Smart Lecture Recorder, a smarter way to automate capturing systems. My name is Talwin and my teammates are
San Kim.
Xiao Fei, Richmond Sua.
Mario Tran.
Let's begin with our problem statement, the purpose of what and why we are doing this project. Remote viewing of lectures given in college courses is becoming increasingly popular among students and professors. At the same time, the lectures can be recorded for subsequent on-demand viewing over the internet. Universities such as Georgia Tech makes lecture available online for both regular and distance education as well as online courses. However, providing such services is often expensive due to the labor-intensive cost of capturing video and pre/post processing. We present a solution to this problem by designing a fully automated smart lecture recorder system that supports capturing automated movements, broadcasting, snapshot feature, zoom, and hand gesture functionalities. Smart Lecture Recorder captures all content of the lecture including audio, video, and presentation material. No camera crew is needed during lecture capture and broadcasting, so the operational cost of the system is negligible. Benefits of this solution will encourage many university professors to be interested in supplementing automated lecture recording systems to their classrooms in order to boost students' learning experience. Next, we take a look at special processes that are needed.
Okay, so in order to make our system work, we have different toolboxes that we had to use. First is Connect. Connect can basically see in 3D. It knows all the 3D locations of the objects. It can process data such as the depth data, skeleton tracking, and etc. And we also use OpenCV. OpenCV, we mainly use it to capture the webcam stream, process the image, and write a video and an image to a file. And this is done through C Sharp and C++. We use C Sharp with Connect since it's the more widely supported language for Connect, while we use C++ for OpenCV. And the main program is all written in C Sharp, and we convert the C++ code into a .dll file where it's accessed on C Sharp. And next, we have Xiaofei to discuss the algorithm. Look.
Okay, this is the algorithm flow. Shows how the whole system works. So the whole system consists of the hardware part and the software part. The hardware part will be the keynet, motor, and the webcam. The software part consists of several functions: skeleton tracking, position status indicator, and gesture processing. Those functions are written in C#. And the functions in the right side, we have a webcam controller. The function inside the webcam controller, we have a snapshot, start and stop recording. This is written by C++. So also we have a data communication between the functions. And more details about those functions will be on the later slides.
We tracked the lecturer using the skeleton tracking by using the Connect to recognize and follow the lecturer actions by getting the skeleton data and the field of view of the sensor as shown on the top left figure. We did this by using C# as a main program to enable skeleton streams so that the Connect can grab skeleton information from the person. We did it using C++ into C# using a C++ class wrapper, which compiles the C++ code into a .dll file. The .dll files are then included into C#, and a thread is created in order to run the DLL files and use its functions. Therefore, this made programming easier and flexible. Then we copied the acquired skeleton data such as the head, torso, leg, or arms into skeleton type variable, which gave locations in X, Y, and Z coordinates. We then convert those coordinates into window coordinate, which created a circle in the window as shown on the bottom right figure. Some of the advantages of using skeleton tracking are unlike the background subtraction method, we do not need the background information before the lecture start. In addition, we did not lose any data since we have the X, Y, and Z coordinate by tracking the lecturer skeleton. Then we can use the tracking to enable motor to rotate left and right in order to follow lecturer. Now Richie will talk about the position status indicator.
So our system has a position status indicator. It has 6 status states. It can detect whether the lecturer is on the left, left, outside right, near or far. So what can this do to us, do to our system? Um, we can directly control the motor using these data, using these indicators.
So, now I'm going to talk about how we are filtering the movement of the lecture smoothly. So when we track the location of the lecture that we have received from the Kinect, the movement of the lecture is not always going to be smooth. This can be a problem because the camera will not be able to move stably to track the lecture. So we have implemented the noise filter called common filter. The common filter will reduce the level of static noises, and more importantly, it will reduce out any rapid changes in the movement of the lecturer. So here's how common filter works. The common filter predicts the movement of the lecturer by using previous location of the lecturer. The common filter then corrects the position by comparing the predicted location of the lecturer and to his actual location. The common filter then repeats these two steps recursively in real time. We have to note that the delay will be inevitable for this common filter because common filter uses the previous position locations.
So as we described earlier, Kinect skeleton tracking can grab the 3D coordinate of the person. Here we calculate the relative distance along z-axis between the hand and the body, and we use the distance to activate the start and stop or snapshot functions remotely. When the lecturer activates the snapshot function, the system will be in the snapshot waiting state until the lecturer moves outside the view. Once the lecturer moves outside the view, the webcam controller will take the snapshot of the board. So also the user can use his left hand or right hand to start or stop the video. The recording. And let's see the real-time gesture control in the video.
Okay, we'll begin by starting the recording. Xiaofei, go ahead and raise your left hand forward to start the recording. Okay, now we notice that the status shows that it's recording right now. Also on the webcam feed that it shows a red word in recording on the top left hand corner. So now we'll test out our snapshot function. So what happens here is the lecturer can give a signal when he wants to take a snapshot of the board. We'll take a snapshot by raising both hands forward. So now we see that the status has shown snapshots waiting. So what this means is that while the lecturer is in front of the view of the board, the snapshot will not be taken until the lecturer moves left or right outside of the view. So now we see that in blue it says snapshot taken. So now we'll test our stop feature. So go ahead and to stop, we'll raise the right hand forward. Notice that our status has shown to stop, and also the recording status on the top left hand corner of the webcam feed it disappeared.
Well, in the future, when we finally implement the rotation of the camera in Kinect, it turns out that keeping track of things such as the position status, distance of the lecturer, and the board becomes a problem. Consider this scenario. There's 3 different positions. The Z distance from Kinect, you notice it changes for those 3 positions. Well, we know it should not. If we want to know if it's near or far from the board, then we need to grab the Z distance from the board. It turns out that currently we're learning that we will need to calculate what they call the plane parameter. The plane parameter and basically defines the normal to the board, and it has 2 properties. If we multiply the plane parameter n times a point Q in the cloud, and if it is equal to 0, it turns out that point Q lies in the plane. If it does not, then it returns a distance from the board. And this is actually what we wanted. And when the camera rotates, we can find the corresponding and normal to the plane if we know the translation and rotation angle.
Although some features have been implemented in the camera system, this system is still far from complete. Major features to be implemented includes clear snapshots, which is the idea of homography in order to fix slight distortions in images when the camera is panning. This allows for quality snapshots of notes when the camera is at an angle viewing another board. Automated emailing, feature which allows for ease of distribution of notes to students where the professor does not have to email them manually. Automated camera movement, a big implementation to the camera system that allows for camera view to follow the lecturer as he or she moves left and right. And last, zoom, a feature to allow emphasis on the lecturer when he or she is speaking. We will want to zoom in on the person's face a bit, and when the person is facing the board, then we can zoom in a bit on the board. Now with an insight into the capabilities and opportunities for the Smart Lecture Recorder capturing system, we conclude our presentation with hopes for greater interest in future upcoming versions of this system.